Today's video is on the subject of propellants used for potato cannons. No, I'm not exaggerating, that's really all it's about. Potato cannon fuel versus muzzle velocity tests at the U.S. Air Force Academy in Colorado, done by several people with the same or very similar name. But let's continue. Acetylene, methanol, butane, ethanol, and propane were compared, and acetylene had a lot more velocity. Now all of these are based on using a see-through barrel and showing how fast the physical object was going through. And yes, they literally used a piece of potato that would fit properly in it. That actually works really, really well, believe it or not, for doing a very high speed. Since it's a low density item, you end up with large numbers to work with, which means you can see lots of variables in it, and you can see any minor differences between, let's say, literally everything here other than methanol and acetylene. You can see slight changes. This allows you to try to find changes when you can't suss them out normally. And then you'd switch back to heavier items so that you could do all of the more powerful items. The idea is to get them into sort of a pecking order, which I've done on the right-hand side. The test conditions was a 46-inch long clear PVC barrel, but they don't mention the diameter of it. And that's a little bit disheartening. That's kind of not what you want. And they use a 772 grain cylindrical raw potato projectile that would fit into it. The maximum ideal barrel length, at least for that diameter of potato and therefore bore diameter, that's why you have a limit on it, was about a meter. It actually peaked almost all of them right around here, so 1 to 1.1 meter for the fuel type. And again, if we don't know the bore diameter, we don't know if that would have affected it at all. Then we get a major improvement in methanol, and then at the top end, we see acetylene not showing any sign of having a peak speed, which means you need to use a longer and longer barrel for testing. The reason you don't use a very long barrel in the first place is you do not want it to peak because of the length of the barrel. You want to find out what length of barrel is optimal. They would need to do another set of tests where they use a 2-meter barrel to see if it keeps reducing, or use I would use a 75% or 750 centimeter long, or 75 centimeter long barrel to see if it suddenly has better performance that way. That can be caused by the back pressure inside of the barrel itself. So anyway, what is the energy level? With propane at 91 feet per second, they had about 14 foot-pounds. Ethanol peaked at about 109 feet per second and 20 foot-pounds. 22 foot-pounds at 113 feet per second for butane. Methanol went up to 158, almost 160 feet per second, and 43 foot-pounds. The max barrel length was tested, but an ideal length was not determined for acetylene, and that was 351 foot-pounds and 453 feet per second. Now, if you can't figure that out, those are really, really low speeds compared to what you would get out of many handgun bullets, for instance. But what you're seeing is a lot of foot-pound rating because it's a 700 grain projectile, like several ounces. We're talking shotgun level here, or at least, close to it. Combustion chamber volume is limited on this, so it affected how much fuel-air mixture they could make. Rich, lean, most and least concentrated, upper and lower limit for flammability. So most fuels only burn over a limited range of concentration, usually pretty low. So you'd have to make it a really big one to test any more variabilities in that. And the ratio where the max energy is produced for a particular fuel or not, and also based on the bore diameter and such, you may not be able to figure it out. That's why you do various lengths and diameters. The propellant amount was calculated to approximate I can't pronounce it, mixture, an ideal fuel and oxidizer or air mixture balance, where both are completely consumed or without excess of fuel or oxidizer after combustion. You're going to have, usually in real world, you'll have to reduce the amount of fuel down below something like 10% usually, or even lower. I'll also have another link that goes to a place that talks about exclusively potato guns because it's a hobby people are into. Now, what does this tell you that's of any practical value? Depending on the propellant and depending on how quickly it burns, or explosively or non-explosively, you will get higher or lower efficiency. That's it. They didn't compare gasoline in here, for instance, because it's much more difficult to get it to vaporize and fire correctly. They didn't do a steam cannon comparison. These are easily put in fuels that are mostly gaseous. Acetylene is a weird one because it's normally achieved by using carbide with water to produce acetylene gas. That's the normal way people do it, and that's how it's been done traditionally in other countries. You put your carbide into a container and then put droplets of water in it. That liberates acetylene, and then that is detonated. Now, what if any practical value is this? Well, first thing is, if it was me, you do more experimentation on length and bore diameter for barrel to figure out how to exploit this most extremely. Next, you'd find out if there's a different optimum for acetylene. Probably is. Gasoline would have different optimums, and same with steam. This is also how you design pistons, the bore for them, how many cubic inches or centimeters, or liters or whatever. And this is also how you figure it out for making pneumatic tubes for sending things through old buildings in the old days, where they would have a little mail chute that would shoot things through with airflow. So, if any of you are curious about this, I hope this video has been useful to you. And it's not just about potato cannons. This can also affect things like launching things into space, or propelling things while you're in space, or just making an air gun work. Thanks for watching. Have a good day. Good luck with that. And this is the data dump for the day.